So in this section, we're going to simplify radicals. There's multiple ways to simplify radicals, and we will talk about them today. Really the most basic way and the easiest way, if you can do it, is to try to recall factors of the terms inside the radicals. So what that means is, for example, here, if I have the square root of 20, and I know that 20 is not a perfect square, but if I can break it into factors of 20, like factors of 20 I know are 1 and 20, 2 and 10, and 4 and 5. And if I look at those, if I can identify some factors of 20 that have a perfect square, I know, or that are a perfect square, then I can break 20 up into 4 times 5. And so I can break it into its factors, and what that becomes is the square root of 4 times the square root of 5, and the square root of 4 is 2. So 2 radical 5 is what's called a simplified version of the square root of 20. Now, if I type square root of 20 in my calculator and I type 2 radical 5 in my calculator, I'm going to get the exact same numeric value because numerically they're the same. However, one is a more simplified version of the other. And so when I have a number in a radical that is not a perfect square, as in this one, I have two choices. I either have to plug it into the calculator and get the decimal form of the answer, which would be 4 point something, or I can get a simplified radical like this, which is what I'm going to want to do. We do a lot of operations with simplified radicals. We can multiply, we can divide, we can add, we can subtract. So we want to know how to simplify a radical to its smallest possible term or look, okay? And we're going to do a lot of practice on this. When you have two separate radicals and they're multiplied together, just like I can take 20 and break it into its two factors that created it, I can also take two radicals like this and actually multiply the numbers inside the roots. So square root of 2 times square root of 3 is the square root of 2 times 3, or the square root of 6. So I can put things together or take them apart in multiplication. And the same thing I can do in division. I can separate something into its factors, or into separate radicals, or I can combine them. So the square root of 10 over the square root of 5 is the same as, for example, I could do square root of 10 over 5, and I know 10 over 5 is 2, so I can make that the square root of 2. Another way that I could do this is I could take square root of 10 and turn it into 5 times 2. And so that becomes square root of 5 times square root of 2 over square root of 5. And anything that is the same, anything divided by itself, is just 1. And so I'm left with square root of 2 this way as well. So we're going to work with putting things together or taking them apart today, depending on what the needs are. We're also going to talk about rationalizing denominators, but we're going to kind of get to that in a little bit. So let's just try to simplify these radicals using the factoring method that I've just shown you. So I'm going to take here the square root of 28, and again, I'm trying to think of factors of 28, right? So 1 and 28, 2 and 14, and 4 and 7. And so again, I realize, oh look, there's 4. So 4 times 7, that's the square root of 4 times the square root of 7. The square root of 4 is 2, and that's fully simplified. 2 radical 7, or 2 times square root of 7. So when you're thinking of your perfect squares, remember that you've got 4, 9, 16, 25, 36, 49, 64. We've got 72. I hope I didn't forget any, right? We've got 100, 121, and there's just so many. But again, you really want to kind of keep thinking of these basic ones because they do come up a lot. When I get to the second one, I've got square root of 48. And so, again, there's a lot of factors of 48 that we could do. I mean, 2 and 24, but there's no perfect square there. There's 12 times 4. So, yes, 4 has a perfect square. But the one that really comes to mind to me is 16 times 3. So, square root of 16 times square root of 3. The square root of 16 is 4. So 4 radical 3 is the simplified version. Now, had I done, for example, 4 times 12, which is doable, right? I would have gotten 2 radical 12. However, this would not have been fully simplified. Notice that 12 breaks down to 4 times 3, and the square root of 4 is 2. And notice that I would have eventually gotten to 4 radical 3, but because I didn't pick the greatest perfect square, I had to work a little bit harder, okay? If there happens to be a number outside the radical, this is just 2 times the square root of 48. So it's going to be 2 times 16 times 3, which is 2 times square root of 16 times square root of 3. The square root of 16 is 4. And I get 8 radical 3. And you don't have to write all the steps out that I'm doing. I'm just writing them all out to show you how I get to the answer. And the last one is 6 times the square root of 45. Well, 45, I can break it into 9 times 5. And I know that the square root of 9 is 3. And it leaves me with a 5 in there. So 18 radical 5, or root 5. And so again, I can do that. Remember, when you're multiplying, you can multiply outside numbers by outside numbers, or coefficients by coefficients, and you can multiply roots by roots. I can't multiply numbers outside to numbers inside. So only the things I pull out can be multiplied like to that 6, okay? Now, another method that was in the example before, or in the list on the previous page, was using prime factorization. And so I do want to go over this method. Now, again, this is not a preferred method, obviously. Prime factorization takes a number like 48 and turns it into its prime factors. And so remember that prime numbers are like 2, 3, 5, 7, and so forth. And basically they're numbers that have only 2 factors, 1 in themselves. So for example, 2. Well, 2 times 24. So 2 is a prime factor. When I get to 24, I have 2 times 12. When I get to 12, it's 2 times 6. When I get to 6, it's 2 times 3. And notice that all these numbers are prime factors. So I'm going to replace 48 by its prime factors. So there's 4 2's and a 3. Notice that if I do 2 times 2 is 4, times 2 is 8, times 2 is 16, times 3 is 48. So if I multiply all my prime factors, they should equal the number I started with. Now, once I break it down to prime factors, I'm looking in this problem, I'm looking for the square root of this number, which means that any numbers that show up twice, I can pull out once. So these show up twice, I pull out another 2. And then I'm left with 3. So notice that I've got 2 times 2 is 4 on the outside and 3 on the inside. And so 4 radical 3 is the square root of 48, and I was able to find it using prime factorization. Now, prime factorization is not my preferred method for something so small as 48. But if I was to get something like the square root of 316 and I was really confused and I didn't know where to even begin with the factors, well, I could do prime factorization and it might help me get to my answer a little bit faster because I might not really remember what all the factors of 316 are. And so I'll do another couple examples like that, but let's at least do some of these examples here. And again, we prefer to do the factoring method, so we want to try to get really good at that. So I've got here I've got 14 times the square root of 75, which breaks down to 25 times 3. I know the square root of 25 is 5, and so 14 times 5 is 70, square root of 3. When I get to the next one, I got 10 times the square root of 125. Well, that's 25 times 5. The square root of 25 is 5. And then there's 5 on the inside. Remember, outside numbers multiply with outside numbers. Roots stay inside with roots. And so 50 radical 5 is the final answer. When I get to 5 and 600, now this one I got to kind of break down. And this might be one where prime factorization might be better for me to do. But let me try to think a little bit more obvious, right? Let me break down 600. I'm thinking 100 times 6. And I know the square root of 100 is 10. And square root of 6 is there. So 50 radical 6. And that's that. And then when I get to 8, I'm multiplying 5 radical 3 times 2 radical 3. And so remember, like I told you, we do coefficients with coefficients or outside numbers with outside numbers. So 5 times 2 is 10. And then we multiply roots to roots. So square root of 3 times the square root of 3 is the square root of 3 times 3, which is 9, and the square root of 9 is 3. So 10 times 3 is 30. So this brings up another common thing, like square root of 2 times square root of 2. If I do it out, it's the square root of 4, and the square root of 4 is 2. So when I have square roots and the two things that are multiplied are the same, when I multiply them, the answer is just the inside number. So like square root of 8 times square root of 8 is just 8. Now, if you want to write the square root of 64 and then break it to 8, that's fine. But again, every time that something inside the radical shows up twice, you can cancel it and pull it out once. And so that's how we get to that. So now we're just going to keep simplifying. We're going to keep doing our work. And you notice here you've got square root of 5 times square root of 5 times square root of 9. Now, your instinct is probably to say, well, I got to multiply 5 times 5 times 5. Or, no, 5 times 5 times 9. And so if you were to do that, 5 times 5 is 25. 25 times 9 is 225. And the square root of 225 is 15. Now, that seems like a lot of work because, truth be told, if you go back to the beginning and you look at it, well, we know that if square root of 5 times the square root of 5 is going to be the square root of 25, and that's going to cancel out to just be 5. Remember, we talked about that. If you have the same number, 5 times 5 times 9, right, twice, that just ends up being one time. So if I have the square root of 5 and the square root of 5 again, then it's just going to equal the number 5. So at minimum, I could have started this problem with just canceling these two out and replacing them with the number 5, and then 5 times the square root of 9. Now the square root of 9 is 3. So 5 times 3 is 15. And so that might have been an easier way to do it. And again, we'll do some others, but in number 10 here, we've got the square root of 11 times the square root of 44. Again, your instinct might be, let me multiply 11 and 44 and see what I get. But the other thing might be just leave it like that and just break 44 down. Notice 44 is 11 times 4. So what we've really got is 11 times 4. Well, anytime something shows up twice, we take it out one time. So 11 times the square root of 4, and the square root of 4 is 2, so it's 22. Same thing goes for number 11 here. 11, and this is 11 times 3. So this is 11 times 11 times 3. Anything something shows up twice, we pull it out. And so the answer to number 11 is just 11 square root of 3. So we always want to work with radicals and things like that. We want to try to work smarter, not harder, right? We don't want to have to multiply 11 times 44 to then rack our brains trying to figure out what the square root of it is. So sometimes it's just better to break everything up into all its pieces and then get the solution that way. When we get to number 12, we've got, again, this scenario where we have 6 times radical 7 over the square root of 35. So I'm going to start by simplifying the square root of 35. I know that that's the square root of 7 times the square root of 5. Square root of 7 cancels out, and I'm going to be left with 6 over the square root of 5. Now here is where, this is a good answer. It's just an unsimplified answer. And the reason that it's unsimplified is because we have to do what's called rationalizing our denominator. A fraction is not simplified if the denominator is ever a radical. So you cannot have a radical or an irrational number in your denominator. So we have to do a process called rationalizing the denominator, which means we have to get rid of that irrational number down there, which is that radical 5. So how we're going to do it is we're going to multiply the top and the bottom by the square root of 5. Remember, we already sort of talked about the fact that if you multiply square root of 5 times square root of 5, you're just going to get 5. So notice by doing that, I rationalized my denominator. My denominator went from irrational to rational. And my numerator will just be 6 times the square root of 5, because we don't really care what the numerator is. It could be rational or irrational. It's the denominator that has to be rational. It cannot be irrational. And so you might say, well, how did you come up with this, right? How did I get square root of 5 over square root of 5? Well, anything over itself is 1. So in essence, all I really did was multiply 6 over radical 5 by 1. It's just by making the 1 in terms of radical 5 over radical 5, I just happen to be able to rationalize the denominator using that method. So it's a pretty common pattern, and we're going to do it so often it's going to be very, habit for you. And then let's go to number 13. And in number 13, we've got 5 times the square root of 48 over the square root of 39. So I'm going to start out by doing 5. I'm going to simplify 48 to 16 times 3. And my denominator is going to be square root of 3 times 13, right? So I know that the 3 and the 3, since they're both inside the roots, those are going to go away. And I know here the square root of 16 is 4. And at the bottom, I've got square root of 13. So right now, I've got 20 square root of 13. So what I'm going to do is I have to rationalize this denominator. So I'm going to multiply top and bottom by square root of 13. And I'm going to get 20 radical 13 all over the number 13. And that's my answer. So we keep doing all these different rules. I'm just going to show you all these different tricks we can do with radicals, right? Another one here, notice that we've got radical 5, or root 5, times root 5 minus 2. Well, this is like a distribution problem. Just because it's a radical doesn't change it. This expects us to do the distributive property. Square root of 5 times square root of 5 is just the number 5, and square root of 5 times negative 2 is minus 2 radical 5. And so you're just going to distribute as if you were doing any other type of number. The radical doesn't change the process, okay? So that's it for number 14. In number 15, we basically just have 3 monomials. We've got 3 radical 2 times negative 2 radical 8 times 3 radical 27. So we could multiply now, and remember that we've got our coefficients. They're going to multiply together. And then we have our roots. And so these would multiply together. But right now, notice how big these roots are. And I don't really want to multiply with those large roots. So I'm going to simplify them first. So 3 radical 2 is fully simplified. Now, negative 2 radical 8 here, square root of 8 is square root of 4 times 2. Right, I got minus 2. And then the square root of 4 is 2. And so this simplifies to negative 4 radical 2. And then I come over to this one, and I've got 3 times the square root of 27. Square root of 27 is 9 times 3. 9, square root of 9 is 3. So I get 9 radical 3. So now I have these 3 terms, and they're a little bit more simplified. So now let me go ahead and let me do my numbers. I'm going to do my outer numbers first. I've got 3 times negative 4, that's negative 12, and I've got negative 12 times 9. So I have negative 108, and then inside the radical, my roots are 2 times 2 times 3. And I know that the 2 2's are going to cancel and bring 1 out, and I'm going to be left with radical 3 inside. So I'm going to get negative 216 radical 3. And there's my answer. Now when I get to 15, again, notice I got that denominator, so I'm going to start simplifying my radicals as best as possible, right? So my square root of 90, I'm going to do square root of 9 times square root of 10, and I'm going to get 15 radical 6. Square root of 9 is 3, and square root of 10. Now, again, just to make my life easy, I could simplify my numbers first here. 3 and 15, that becomes 5 radical 6 over 1 radical 10. I don't have to write the 1. And then the last thing I'm left with is this 10 in the denominator, so I'll do square root of 10 over square root of 10. And I should get 5 times the square root of 60 all over 10. And again, look at my 5 and my 10, right? That simplifies, so square root of 60 over 2. Remember, anything that's outside the radical can simplify with an outside and insides with insides. And now I guess I just need to figure out, well, can I simplify radical 60 anymore? And I know that it's 4 times 15 over 2. And that's 2 radical 15 over 2. And notice the 2's cancel. And so I'm left with the square root of 15 as my final answer. So there was a lot going on there. I did a lot of simplifying along the way. I probably could have just waited and done it all at one shot at the end. And that might have been maybe a little bit easier. Or just, I don't know. I like just chipping away at the numbers as I go. I'm going to move this over. Whoops. Sorry. So this ended up being the square root of 15 was the final answer. And then here, notice that we've got 8 radical 3 minus 6 radical 3. And you can treat radicals like variables. If I told you this was 8a minus 6a, you would tell me the answer is 2a. That you would just do 8 minus 6, and the a would be the same because these are like terms. Well, same thing goes for like radicals. And so when you have radical 3, your final answer will have radical 3 in it, and it'll just be 8 minus 6 or 2. And so 2 radical 3 would be the answer there. So we come over here and we've got to simplify all these, and we're going to have to try all of our rules again and just kind of really know what we're doing. So again, the first thing we're going to do is look at it. It's a subtraction problem. So I'm going to kind of see, well, do I have like radicals? And I realize that I don't. But I also realize that my radicals aren't simplified. And so really to make this determination, I'm going to have to simplify my radicals. So 24 is 4 times 6. And I know the square root of 4 is 2. 6, so I get negative 4 radical 6. So now I have minus 4 radical 6, minus 3 radical 6, and now notice that I'm dealing with like terms. So my final answer will be negative 4 minus 3 or plus negative 3, so negative 7 radical 6. And that's how we get that answer. Again, here I'm doing an addition problem, but my radicals are not simplified, so I'm going to need to do that. So this is 3 times the square root of 9 times 5. The square root of 9 is 3. And so this left one simplifies to 9 radical 5. The right side is 7 times the square root of 36, which is 6, so it's 42. So I have 9 radical 5 minus 42. And that's all I can do. I cannot do anything else. That's as far simplified as I can go. Again, I come over to 20 and I do the same thing. I'm going to simplify this 3 radical 32. This is equal to 16 times 2. The square root of 16 is 4. So I'm going to get 3 times 4 is 12 radical 2. And then here I've got 4 times the square root of 63. So that's 9 times 7. Square root of 9 is 3. 4 times 3 is 12 radical 7. And so I've got, here's my problem here. It's 12 radical 2 minus 12 radical 7. And there's nothing else I can do. Whoops, radical 7. That's just my final answer. I can't combine the radical 2 and the radical 7, so I'm totally done. Now here, if you look at it, we've got a problem. It's a binomial times a binomial. I've got 4 plus radical 11 times 4 minus radical 11. And one of the things you should see is you should notice that this is like what we learned before. This is your a plus b. You learned this in Algebra 1 times your a minus b. Notice that the first terms are the same. Your a is 4. Your second terms are the same. Square root 11, square root 11. Those are b. And what you have is just a sign difference. So sum and difference of squares. So what's going to happen is you're going to, when you go to FOIL this, if you did this, your final answer would be a squared minus b squared. Because the middle, it's basically first times last times last. The O and the I in FOIL kind of cancel out. So I'm going to show you this one doing it the long way, foiling it the long way. However, you're going to probably not want to FOIL this out every time. You're going to want to recognize that it's a difference of squares. So again, if I do the FOIL method, right, it's going to be first times first, 4 times 4 is 16, outer times outer, minus 4 radical 11, inner times inner, plus 4 radical 11, and last times last, positive radical 11 times negative radical 11 is going to equal negative 11. Notice the middles cancel because it's minus and plus the same thing, and you get 16 minus 11, or 5. And so that's going to be your final answer in this one. It's just 5. So again, if I remember that little pattern, if you remember to do, because it's the a squared minus b squared scenario, a is 4, and b is square root of 11. And you see that 4 squared is 16, and the square root of 11 squared is 11. And again, you can get the answer pretty quickly without having to do the whole foiling. Okay? And so now we go to this next one. Now this is not exactly the same thing, because notice that this is 3 radical 7 minus 3, or minus square root of 3. So this is it, but it's times itself twice. So it's the same thing, the whole thing, times itself. So now I have to kind of FOIL this, because again, it's a binomial times a binomial. So I'm going to have to do first times first. 3 times 3 is 9, and square root of 7 times square root of 7 is just 7. So it's going to be 63. Then I do outer. So I'm going to do minus 3, right? And then square root of 7 times square root of 3 is square root of 21. Then I'm going to do inner. And so again here, I'm going to get minus 3 square root of 21. And then I'm going to do last times last, which is going to be minus 3. So it's going to be minus square root of 9, which is 3. And so notice here, the middles don't cancel out. They end up doubling. So I get minus 6 radical 21, minus 3. My outer and my first term are like terms. So 63 minus 3 is 60, minus 6 radical 21. And that's it. Radical 21 can't be simplified, and that's going to be my final answer. So there's just a lot going on here. It's a long lesson. A lot of this should be repetition, but there is a couple new concepts. And one of the new concepts, rationalizing the denominator, we just did that when the denominator is a square root. So square root of 2, square root of 2, and we get 5 radical 2 over 2, and that's simple. Just multiply by whatever this is, and that way it gets rid of that radical. However, what if the denominator is an expression? What if it's an expression that contains a radical? Well, if I just multiply by radical 3 over radical 3, right, you think, oh, well, that's going to work. Well, notice what happens. When I do it, I'm going to get, basically, it's like distributing radical 3 to that, and it's going to be 2 radical 3 plus square root of 3 times square root of 3 is 3. But notice what happened. I didn't get rid of the radical. I just moved it. I moved it from one term to the other, but I still have a radical. So this method is ineffective for this strategy. So what do? Well, this is where you're going to use conjugates, okay? And a conjugate is basically the same expression, but with a different sign, okay? So if, for example, you have 2 over 2 plus radical 3, you're going to multiply by 2 minus radical 3. And you're going to do the same thing. Whatever you do to the bottom, you do to the top. And so you might say, well, how does that work? Well, notice that if you do 2 plus radical 3 times 2 minus radical 3, that ends up being that sum difference of squares, right? That's going to end up giving you, remember, that's going to be a squared minus b squared. Well, a squared is 2, so you're going to get 2 squared, and it's going to be minus b squared. Well, square root of 3 times square root of 3 is 3, so it's going to be 2 squared minus 3. So it's going to leave me with 4 minus 3, or 1, and my denominator is rationalized. So now I just do the same to the top. I do 2 times 2 minus radical 3, so I'm going to distribute the 2. 2 times 2 is 4, minus 2 radical 3, so 4 minus 2 radical 3 over 1, or just 4 minus 2 radical 3. And that's it. My answer is done. So now we'll practice rationalizing a few denominators, and I think we're good. So let's start with this top one. Now notice the denominator is just a single radical, or single square root, so we're going to do square root of 3 over square root of 3. So again, at the top, outside numbers by outside numbers, assume that's a 1. 7 times 1 is 7. And then radical 2 times radical 3 is radical 6. And the denominator, square root of 3 times square root of 3, is just 3. And we're done. I can't simplify this 6 with this 3. And the reason I can't do that is because they're not I can't simplify roots with outside numbers. Okay, so that's as far down as I can go. Again here, same thing. I'm going to multiply square root of 3 over square root of 3. My denominator just becomes 3. And my numerator, I'm going to have to distribute this radical 3. So it's going to be 4 radical 3 plus radical 6. And again, I can't simplify any further. This is my final answer. I'm tempted because I see a 3 there and a 3 here. I see a 6 and a 3, and I know they're factors, but they have common factors. But I just can't do it because the 3 and the 6 in the numerator are in the roots, as opposed to the 3 at the bottom, which is not in a root. And then here I've got an expression, so I'm going to multiply by a conjugate. So I'm going to multiply the top and bottom by 3 minus radical 2. And I'm going to do so by numerator, 1 times 3 minus radical 2 is just going to be 3 minus radical 2. Anything times 1 is itself. And my denominator will be the first term squared minus the second term squared. So square root of 2 squared is 2. So I'm going to get 3 minus radical 2 over 9 minus 2. And that's going to be 3 minus radical 2 over 7. And I can't simplify any further, and that's my answer. And my last one, again, I'm going to multiply it by the conjugate. 1 plus radical 2 over 1 plus radical 2. And I'm going to have to FOIL my numerator because those are not some differential squares. So I'm going to have to do first times first is 3. Outer times outer, 3 radical 2. Inner times inner, 1 radical 2. And last times last, 2. And my denominator is going to be, again, first number squared minus the second number squared. And so I'll just simplify here my final. So 3 plus 2 is 5. These two are actually like terms, so that's going to be plus 4 radical 2. And 1 minus 2 is negative 1. Now here, that's one way to leave the answer. The other thing I could do is I could just make the negative 1 up here, okay? And I could also distribute the negative 1. So minus 5 minus 4 radical 2. These 3 answers, this is answer number 1, this is answer number 2 here, and this is answer number 3. And to be truthful, they all equal the same and they're all valid. This is probably the preferred method because we don't like denominators, especially negative denominators. But they all equal the same thing. And that's it. So that's the rule, again, of rationalizing a denominator with a square root and rationalizing a denominator with a radical expression like 3 plus radical 2 or 1 minus radical 2.